Welcome back, everyone. In this lecture, we're going to be talking about cost functions, which is going to allow us to measure how far off we are in the output predictions of our neural network. And then we'll talk about gradient descent, which is going to help us minimize that cost or minimize that error. So often cost functions, you also hear them labeled as loss functions or error functions. So we're going to talk about all that, a really interesting topic here. And it really fundamentally is going to help us understand better how the neural network will actually learn. So we already understand that neural networks, they take in inputs in that first layer, then they multiply them by weights and then add biases to them, and then maybe that gets passed on through an activation function like the sigmoid function or the rectified linear unit, and then that ends up going into another layer, and then you add another set of weights and biases, and so on, all the way to that last output layer. So that last output layer, we can maybe call that or refer to it as y hat. That's essentially the model's estimation of what it predicts the label to be. And so we have two main questions. After the network creates that prediction, how do we actually evaluate it against the true label? And then after the evaluation, how can we update the network's weights and biases? So really what we're going to focus on this lecture is how do we evaluate how far off our prediction is. For updating the network's weights and biases, we'll have to learn about backpropagation, which is coming up in a future lecture. So right now let's focus on that first question. So what we need to do is we need to take the estimated outputs of the network and then compare them to the real values of the label. And keep in mind, what I'm referring to right now is happening during the training or fitting portion of the supervised learning process. So right now what we're doing is we're using just the training data set. That way we can go back and update our weights and biases. During the test set, we're not really updating weights and biases. Instead, we're just, again, evaluating overall on the entire data set, how does our neural network perform? Right now, we're doing these small evaluations on these training batches in order to actually then go back and update weights and biases in our network. So keep that in mind. Okay, so in order to actually compare our neural network's output to the true value, we're going to be using what's known as a cost function. And this is also often referred to as a loss function or error function. Essentially, it's just something that measures how far off you are from the true value based off your prediction. And one important caveat is it should be an average. That way it can output a single value. Then you can keep track of that loss or cost during training to monitor network performance. So hopefully during each epoch of training, your loss or cost goes down, down, down until you kind of like converge to a minimum cost value. So what we're going to do here is I want to introduce a couple of variables. We're going to be using y to represent the true value, and then we'll be using a to represent the neuron's prediction. So in terms of weights and biases, what we have here is, recall, we set z to be a representation of weights times x plus b. And then we pass that z into an activation function, such as a sigmoid function, so that z passed into the sigmoid is then equal to a. So all I'm trying to say here is that A represents kind of that final output of a neuron, which takes into account what the activation function was, and that also then takes into account Z, which in turn takes into account W, which are the weights and the biases. So A, just keep that in mind, holds a lot of information. It holds information about the activation function, the weights, and the biases. So probably the most common cost function you'll see is known as the quadratic cost function. And if you've done any machine learning, this probably looks really familiar to you because it looks like root mean squared error, which is kind of essentially what it is. Here it's just notated for multidimensional data. So all we're doing here is at the end of the day, we're calculating the difference between the real values. Here we label it y of x. So if you have some x input, we specify y as the true function. So that would be the true value. And then we're subtracting our predicted values. So here we have a of l of x. And keep in mind that a of l, that notation just signifies that that is the activation function output of the L layer, where L is your last layer, which means the layer before that in the network is L minus 1, then the layer before that is L minus 2, and so on. Later on, we'll see why it's more convenient to kind of mark L as your last layer and then work backwards from there instead of starting from the beginning. So again, A of L of x, that's essentially your predicted output. So keep in mind the notation again shown here kind of corresponds to vector inputs and outputs, since we're really dealing with a batch of training points and predictions as we go along. But the main idea is you have C as the cost function. you're doing some sort of averaging, so that's why you have 1 over 2 times n. So n is the number of points there. Then you're taking the sum of all those differences and squaring them. So a really common question is, why are we actually squaring this? And it does two useful things for us. One, it keeps everything positive, because whether you have a positive error or a negative error, if you square it, it becomes positive, which is good because we want some sort of absolute measurement of error. If we weren't squaring this and we had stuff that was negative and positive, when you average it out, that could hover around 0, which is actually not a true indication of the absolute value or absolute units of how far off you are. So squaring it makes sure that everything's positive. The other and much more important thing it does is it's going to punish really large errors. So sometimes you have some data points that you're going to be really off on. And if you actually square that error, then it exponentially grows as terms of your cost. So maybe you're off by $10 in whatever units you're trying to measure, but your cost is going to report that in units squared. So it's going to say you're off by 100 instead of just 10. So you're going to really punish your network for being really off on certain points, which is good because you don't want your network to suddenly be able to not predict well on even just a few points where it gives you a huge error. You'd rather suffer a little bit on all the other points and not be totally off on those few kind of edge cases. So that really helps punish large errors. Now in general, we can think of the cost function as a function of 4 main things. So the cost function is going to be a function of W, which is our neural network's weights, B, which is all the biases in our neural network, S of R, which is the input of a single training sample, and E of R, which is the desired output of that training sample. And that makes a lot of sense because the cost is dependent on what the current weights and biases are. It's also dependent on what you passed in as the actual training example. And then it's also dependent on what you're comparing it to, which is E of R. So notice how that information was actually all encoded in that simplified notation that we had. So I showed you this as the cost function. And you may be wondering, didn't you just say that the cost function is a function of W and B? Where's W and B in the quadratic function here? Well, it's actually encoded within A of X. Because remember, A of X holds information about weights and biases because A of X is Z passed into the activation function, where Z then contains information about W and B. Okay, so this means that if we have a huge network, we can expect the actual cost function to be really quite complex, with a huge vector or tensor of weights and another huge tensor of biases. So for example, if we were just to take a small network and start labeling every weight and every bias and every output as kind of the output of the activation function, which is A, you can see all the parameters labeled here. It can get really complicated really fast. And this is a really small network. There's only kind of 4 layers here, 2 hidden layers, and those hidden layers aren't even that big. But you can see here, if we start notating everything, it can become quite complex. You already have quite a large matrices of weights and biases. So how do we actually calculate this? How do we calculate that cost function and then figure out how to minimize it? So in a real case, this means that we have some cost function C dependent on lots of weights. That cost function is going to depend on the weight of that first input, then weight a second one, weight on third one, all the way to W of n. And what we need to do is we need to figure out which particular weights lead us to the lowest cost. Because we want to go back here and figure out for all these weights, how do I change them to minimize my cost function at the very end? So for simplicity, and in just thinking about this, let's imagine that we're dealing with a really simple network that only has a single weight, essentially just one neuron. So what we want to do is we want to minimize our loss or cost, essentially our overall error. Which again, that means we need to figure out what value of W do we use that's going to result in the minimum of C of W. So here is our plotted out really simple cost function where it's a really simple network. It only contains one weight. Well, what we want to do is we want to figure out what value of W minimizes this cost function. And while this is a really simple example, you can probably just tell that in order to minimize the cost function here, you can see that the minimum probably falls somewhere where that arrow is. So that's the weight that is going to minimize that cost function, which means that's probably the weight we want in the actual neuron or that input to the neuron, because that reduces the cost to its minimum. Now, students of calculus know what we could do is we could just take the derivative of this cost function and then solve for 0. But recall, our real cost function is going to be super complex, and it's not going to be one-dimensional, two-dimensional, or even three-dimensional. If you take a look back at that network, it's going to be as many dimensions as there are W, and that's not even something I can actually plot. So again, it's going to be n-dimensional, which means taking that derivative and setting it equal to 0 is actually not going to be, you're not going to be able to calculate that without spending kind of 1,000 years of computational time. So our networks, especially when we build out really large networks, are going to have thousands of weights to them, hundreds of weights. We're not going to be able to take that derivative. So instead, what we need to do is a stochastic process. So what we can do is we can use gradient descent to solve this sort of problem. So let's again go back to this kind of simplified version of our network where we just have one weight and see how gradient descent would work on this simple example, and then we can easily expand it to more complex examples. So what we do is we just start off at one point on this cost function. And again, what we're searching for here is that W value that minimizes this cost function. So what we do is we calculate the slope at one point, and then we move in the downward direction of the slope. And you keep repeating this process until eventually you're going to converge to 0, indicating a minimum. So what we could have done is, keep in mind, we could have changed our step size to find the next point. So here we kind of took equal step sizes. And if you take smaller step sizes, it takes longer to find the minimum. If you take larger step sizes, you'll go faster, but what happens is you risk overshooting the minimum. So if you go too large of a step size, you may actually miss that minimum weight or minimum weight tensor and then kind of overshoot and you don't end up converging. So that step size is known as the learning rate. So if you ever see in neural networks that they're editing the learning rate, what they're really doing here is they're editing how fast they're going to try to find that minimum weights value. And it works the same for biases. You're finding those minimum weights, really the values of the weights and biases that minimize that cost function. Now in those previous examples, something you should know is that the learning rate was constant. That is to say, each step size was equal. So regardless of which one we're actually looking at, such as the smaller step sizes or the larger step sizes, the actual step is equal for all of these. Now, we can actually be a little clever and adapt our step size as we go along. You can imagine that since you're starting off kind of in a random position in this n-dimensional space of possible weights and biases, if you start with larger steps, what you can do is you can then go smaller and smaller in your step size as that gradient or that slope gets closer to 0. And this is known as adaptive gradient descent. Depending on that gradient you get back, you're going to adapt your step size. So in 2015, Kingma and Ba published their paper called ATOM, a method for stochastic optimization. And ATOM is a much more efficient way of searching for these minimums. So you're going to see us actually kind of sometimes state ATOM as our optimizer during the code. So keep that in mind. If you ever see ATOM, all we're really referring to is this optimized way of performing this gradient descent, where we have kind of this adaptive step size. So we kind of start off large, and then depending on where we are, we maybe go smaller and smaller. So you kind of get the best of both worlds. You get to use the larger step sizes and kind of speed up finding that minimum. But then as you get closer and closer to it and you don't want to overshoot, you can go with smaller step sizes. So you can actually then compare ATOM versus other gradient descent algorithms. And here it's showing you the training cost versus iterations over the entire data set. And you can see ATOM here is outperforming these other adaptive gradient descent algorithms. So all the ones listed here that are not ATOM, they're also actually adaptive gradient descents. However, ATOM performs better than all of these. So what we're going to be doing is we'll be using ATOM since it's really quite common to use it for neural networks. So if you ever see that, all we're doing here is we're kind of saying, okay, optimize the way we find this minimum. Now realistically, we were showing you that illustration of gradient descent on just a single W. So that was kind of one-dimensional W. What we're really doing is we're calculating gradient descent in an n-dimensional space for all our weights. Here you can see calculating gradient descent in a two-dimensional plane, including the weights and the bias. realistically, I'm not even going to be able to illustrate the n-dimensional space because it's going to be n dimensions of tens or hundreds of weights and biases. So there's really no way we can illustrate that for you, which is why we simplify it down to kind of a single weight. You can understand what gradient descent is doing, and then what we're actually doing, or what the computer will be doing for us, is doing the same sort of calculations, but on an n-dimensional space that we can't really realistically illustrate for you. So when dealing with these n-dimensional vectors, otherwise known as tensors, the notation changes from derivative to gradient. So that's why you've heard me say gradient a couple of times instead of the term derivative. So when we're dealing with n dimensions, instead of saying the derivative, then actually the correct term becomes gradient. And so that means we calculate the gradient of the cost function with respect to all these weights. So if you see that upside down triangle, that's essentially kind of the way you notate gradient instead of just saying derivative. Now, before we finish up and wrap up this lecture on loss or cost functions and gradient descent, I want to quickly mention that for classification problems, instead of using the quadratic cost function, what we end up often using is the cross entropy loss function. And what's nice about this cross entropy loss function is that basically what it does, it assumes that your model predicts a probability distribution for each class. So maybe it has a distribution for class 1, class 2, class 3, and so on. And the way this formula actually works out is for a binary classification, that is only two classes, you have the top formula resulting, and then those logs actually represent natural logs. And then for m number of classes greater than 2, you end up using the formula below. And you don't have to worry too much about this formula because essentially when we're coding it out, we're just going to specify use cross entropy. So when we're performing classification, especially multi-class classification that's greater than just binary classification, we'll be calling upon cross entropy to be our cost function. Okay, so just keep that in mind. If you ever see us coding and we specify cross entropy, these are the actual formulas we're specifying the computer to use in order to figure out a probability distribution for each of those classes. So as a quick review, we talked about cost functions, we talked about gradient descent, we talked about the fact that there's different optimizers like the atom optimizer, and then we also talked about quadratic cost and cross entropy. So far, we understand how networks take an input, affect that input with weights and biases and activation functions to produce an estimated output. Then we learned how to evaluate that output against the true labels. The last thing we need to do in our theory discussions is the following question. Once we actually get that cost or loss value, we understand how far off we are. We still haven't really talked about how we go back and adjust all those weights and biases. That's still kind of this magical thing. And that magical thing, in just a second, will no longer be so magical. Instead, it'll be mathematical. And it's called back propagation. You essentially propagate backwards through your network and then update all those weights and biases. So that's exactly what we're going to cover in the next lecture. I'll see you there.